Okay, let's start. Next speaker, Nataliia Luno from Vinnytsia. Let's start.
Dear colleagues, I'm apologize for having problem with internet connection. My report is called Connection Problems for the Generalized Hypergeometric Appell Polynomials. Let's start from what is connection problem for two given polynomial sequence. The problem of connection is to find the unknown coefficients C, E in the right-hand sum of the equality pair Pn of x equals and so on. If one of the sequence is the representatives of the standard basis, the connection problem is called the inverse problem, and here you see the equation. Let us recall that the Appell polynomials forms the Appell sequence, which and every member of which satisfy the simple recurrent equation. Here you see a new Appell type polynomial sequence. It was presented and it's not yet publicated, but it's going to be publicated in the first number of this journal. Let's start from the definition of that polynomial sequence. As you see,
Наталя, у вас пропав екран. Покажіть.
мене пропав екран?
Так, покажіть, будь ласка.
Зараз. Just a moment. Share screen. Share screen. Видно?
Да. Видно.
Так, видно, так? We present a new Appell sequence. Here you see Rn superscribed, and it is defined via generalized hypergeometric function with joined set of quotients. This Appell sequence has, as every arbitrary Appell polynomials, has also generating function representation. When we multiplied exponent of x and t by the series of a of t. And the generating function of the Appell polynomials was found in the article showed here. And this generating function has form 1. Now we are going to apply the approach proposed in the article of Benchek and Chagara, connection problems via lowering operators. The fact is that if you have two Appell polynomial families Pn and Qn with respective transfer formal series A1 of t and A2 of t, then you always can define the unknown coefficients in the sum of in the right hand. And these coefficients alpha n, we may say alpha n minus e, is always series quotient. So here we call this part the formal series powers A of formal function. And it is known, it is a well-known fact that a formal series is invertible even only if the first member of this row is not equal to 0. And in that case, the inverse of this formal power series could be computed as the formal power series, which coefficients Cn are defined recurrency. Here we have the denoting for A and B as a Polynomial symbol or rising factorial. The proof is easily to be obtained. So using this lemma, we have the closed form of the generalized hypergeometric Appell polynomials, and we have the solution of the inverse problem for those polynomial sequence. But as we see, the solution of the inverse problem is given recurrency. It is should to be said that the generalized hypergeometric Appell polynomials is the generalization of well-known Gould-Hopper polynomials. It is right to write as here Gould-Hopper polynomials. The Gould-Hopper polynomials have transfer function in the form of exponential function, and as a sequence it has a simple inverse 1, the same exponential function just to a negative power. And then for the Gould-Hopper polynomials, the solution of the inverse problem is much more simpler than for the generalized hypergeometric Appell polynomials and have the closed form. There are no recurrences here. There are some other cases when the solution of the inverse problem could be defined in a closed form. In that cases where when you know the inverse series. For example, if we have Bessel function in the form of the confluent generalized hypergeometric function, we know its inverse, and thus we know the formula, the explicit formula for the inverse problem for such such form of the generalized hypergeometric upper polynomials. To solve and to prove this lemma, which is without the number, we use the simple method of equating the equal powers of t, and proceeding the same, equating the equals powers of t, we can find the solution of connection problems for some another Appell type sequences. For example, we found the solution of the connection problem between the generalized hypergeometric Appell polynomials and the Bernoulli bonds. As we see, the solution has the closed form, and also we derived the solution of the connection problem between two different generalized hypergeometric polynomial families. If we have the explicit form of the first family and the explicit form of the second family, then we can define the connection coefficients, which is denoted by gamma e, and here is the recurrence equations for gamma e. Using the same straightforward approach, which deals with generating or a transfer function which is the same, we also derived the recurrent equations for arbitrary generalized hypergeometric polynomial family, and this result is new. As you can see, the recurrence equation have n over k multiplied by k and plus 2 summands, but the coefficients in these equations is also defining in a recurrence way. I can also do not see. I can also add that where we finished. Yeah, I can also add that in the case of the Goldhopper polynomials, the recurrent equations is also known. It was published in the last century, and the recurrent equation has the form as you see in the corollary 2.8, and in addition the Goldhopper polynomials satisfy the nth order differential equation. The same we can state about the generalized hypergeometric Appell polynomials, that this polynomial family is also satisfy a differential equation, and as a consequence, as an example, the Hermite polynomial is a partial case of Gold-Hopper polynomials, and the recurrence equation for Hermite polynomials is also are obtained from our results. I think this is all.
Okay.